A somehow unpopular technique is needed in this integral. So we have this integral, and the technique is trying to create a double integral and then interchange the integrals and then solve it. So let's see how we use that in this problem. If you don't know about erfc function known as complementary error function, let me give you a slight introduction. So basically, let's say if you have integral from 0 to infinity of e to the power minus t square dt, e to the power minus or t square dt, this is equals to root pi by 2. You might know about the popular Gaussian integral, and you can also solve for it. And if this is going from 0 to x only, yeah, and not up to infinity, this is slightly lesser than root pi by 2. It depends on x, and so there's some error which can be written as rf of x. Yeah, so there's a factor which goes from 0 to 1, and this is the rf function depending on the x. Now if it goes from x to infinity, this is just complementary to the error this integral, so that's why we write it as root pi by 2 times complementary error function. And note that the error function of 0 is just 0 because it goes from 0 to 0, and complementary error function of infinity is also 0 because it goes from infinity to infinity. Okay, now let's begin the integral. So we can start the integral by writing the integral from this function. So this is 2 by root pi times integral from x to infinity of e to the power minus t square dt, and then this is e to the power minus 2x square dx. Now let's interchange the integrals. No, but before that, we can try to make this integral a numeric one. And how do we do that? For that, we can let y equals to t by x, yeah, and that will simplify the limits of integral. So we have 2 by root pi integral from 0 to infinity, integral from now 1 to infinity, and t equals to yx, so minus x square y square, and for the world of t, x is constant, so we can write this as x dy. And over here we have e to the power minus 2x square dx. Now we can interchange the order of integral, and then that will simplify the integration process. 1 to infinity, 0 to infinity, x times e to the power minus x square y square plus 2, now dx dy. Now to simplify this integral, we can make it 1 by root pi and take the 2 inside, yeah, and so we can have e to the power minus x square y square plus 2 times 2x dx and then dy. I'm doing this because if we let y as x square, 2x dx will just be dy. So this is e to the power minus y times some y is already there. So if I let m as x square, it will be dm, and then it will be e to the power minus m times some constant, and that's easily integrable. Yeah. So that's why we can make this as 1 by root pi integral from 1 to infinity and e to the power minus x square y square plus 2 by minus y square plus 2 from 0 to infinity and then dy. Now for this, I can write this as 1 by root pi and the integral from 1 to infinity. At infinity this is 0, minus minus plus 1 by y square plus 2 dy. Now I can write this as 1 by root pi. This is just 1 by root 2 tan inverse y by root 2 from 1 to infinity. Okay, so this is 1 by root 2 pi. Tan inverse infinity is pi by 2 minus this is tan inverse 1 by root 2. And we know that tan inverse 1 by x is just cot inverse x. So let me write this as cot inverse root 2. Yeah, cot inverse root 2. And we know that pi by 2 minus cot inverse x is just, okay, yeah, pi by 2 minus cot inverse x is just tan inverse x. So this will be just the tan inverse x, and that is tan inverse root 2. So I guess this is the answer. Yeah, this is the answer. Now, in the beginning of this video, like I was thinking that this method is quite good and this method is really helpful for solving this integral, and other methods like integration by parts will be really tough, and other methods will also be tough other than this one. But in the beginning of this video itself, I noticed that this could have been more easier if I use Feynman's technique. Yeah. So I could do something like this. I can say I of a is equals to integral from 0 to infinity of a complementary air function of ax e to the power minus 2x square dx. Now in this way also I can do it actually. And then if I take I dash of a integral from 0 to infinity, now this is just 2 by root pi times e to the power minus a square x square times x, yeah, and this is e to the power minus 2x square dx. This x is from the chain rule and this is from the definition of erfc function. So now this is I dash of a. I can take a 1 by root pi outside. Now you can notice that this is just similar integral. So that is almost same because we are taking this integral outside and differentiating. I mean taking it outside and then integrating. So it is same as differentiating inside. Now basically later on we will integrate. So it's actually kind of same. Yeah. So we have now. I can take minus 1 outside. Is it? Okay, so this is basically minus 2 by root pi. I'm sorry for that. This is multiply. Okay, so anyways, I did get the minus sign. So this is minus 2 by root pi. And the reason is because erfc of ax is integral from ax to infinity, yeah, of e to the power minus x square dx. So that's why so there will be something at infinity and something at ax, and that will be a constant. So if we differentiate this over here in the first limit, that will just be 0, and in the second one we will have minus x square. So that's why we can see it from the from the fundamental theorem of calculus. You can notice that thing. So minus 1 by root pi and then 0 to infinity, and e to the power minus x square a square plus 2 times 2x dx. Yeah. After this, you can have I dash of a is equals to, sorry for this, is equals to minus 1 by root pi. So this is now again the same thing, e to the power minus x square a square plus 2 by a square plus 2 from 0 to infinity. So now we have I dash of a as minus 1 by root pi. Now this is 0. Okay, so I do have minus 1 over here. I'm sorry for that again. This minus 0 plus 1 by a square plus 2. Now if I integrate this to get I of a, we have minus 1 by root pi. This is 1 by root 2 tan inverse a by root 2 plus c. Now I earlier told that if I substitute a equals infinity, or c of infinity is 0. So overall integral will be 0. That means I of infinity will be 0. So to find out I of infinity, we have minus 1 by root 2 pi tan inverse infinity is pi by 2 plus c, and this is 0. So that's why we will have c is equals to now pi by 2 root 2 pi. Yeah. Yeah, nice. So that's why I of a is equals to minus 1 by root 2 pi tan inverse a by root 2 plus pi by 2 root 2 pi. Yeah. Now the answer is actually the I of a. Yeah. I have 1. Yeah, that's why substitute a as 1. You get I of 1 as minus 1 by root 2 pi, or tan inverse 1 by root 2, plus this is actually, I can write this as pi by 2 by root 2 pi. Now this is because now I can take root 2 pi as common, and this will be pi by 2 minus tan inverse 1 by root 2. Now they are similar thing. First of all, I can change tan inverse 1 by root 2 to cot inverse root 2, and then pi by 2 minus cot inverse root 2 as tan inverse root 2. So we will have tan inverse root 2. And yeah, that's the answer. The answer is same. Of course, it should be same because it's mathematics and not politics or other philosophical stuffs. Where two different perspective give different answer. Here's always the same answer, and that's the beauty of mathematics. And like, there's also beauty in tutoring, because only from the tutoring I noticed that there's other way as well. Maybe I would have noticed if I spent a lot of time as well, but here the tutoring helps like activate different parts of the brain, and like it kind of helps to compete faster than in normal times. Maybe that's just the mechanism of body, but that does. So yeah, I'm happy with what I'm doing. I think you are happy with the solution as well. So yeah, hope this gave you a good exercise. Thanks for watching. Look forward to seeing you in the upcoming videos too.